Okay, so for the first topic that I'm going to cover, I'd just like to do a quick review of some things about functions, which you've probably seen in previous math classes. So first, just as a reminder, a function is just any rule that associates some output to the given input. And the important thing is that that output has to be unique, so it associates a unique output. So what does this mean? For example, if we have a function f of x equals x squared, then your input could be some number like 1, 2, 3, 4, and your outputs corresponding to these numbers would be 1 squared, which is just 1, 2 squared, which is 4, 3 squared, which is 9, and 16. So basically, all a function is some rule where you take a number, plug it in, and it spits out some other number, and it gives you exactly one number. So an example of something that would not be a function would be y squared plus x squared equals 1. If you're not familiar with this, this is the equation for a unit circle. And the reason this is not a function is, well, first of all, it's right now as x and y on the same side of the equation, so we try to solve for y. When we do that, we get y squared is 1 minus x squared. And if we take the square root of both sides, then we get y is equal to square root 1 minus x squared, but it could have a plus or minus sign. And so because of this plus or minus sign, we have two possible outputs for any given x value. And this means that this would not be a function. So if we draw graphs of these two things, x squared gives us a usual parabola, and this one gives us a circle of radius 1. And so one thing you may recall is that if we have the graph, we can quickly tell if something is a function or not by using something known as the vertical line test. So basically, you draw in a bunch of vertical lines, and if these lines intersect the graph at only one point, then we do have a function. But in the case of this circle, if we try to draw a vertical line, then we see there's 2 points of intersection, and that means that this fails the vertical line test. And that's one way we can quickly determine that this is not a function. Okay, so this is just a quick review of what a function is. And two things that are important to keep in mind with functions are the domain, which is the set of all possible inputs to the function, and the range of the function is the set of outputs for the domain. Maybe a better way to say this is the set of outputs for the numbers in the domain. So, for example, let's look at f of x equals x squared. The domain would be all real numbers, because we can plug in any number we want this function, 1, 2, -1, 0, and it gives us an output. Everything is well defined and there are no problems. The range, we know that for any number we plug in, when we square it, we're going to get a positive number. So that means that for this, we get all numbers greater than or equal to 0. And we can get 0 if we plug in 0 to the function, of course. So that's that function. What about a different one? F of x equals 1 divided by x. So for this function, the domain is almost all real numbers again, but we see that there's a problem if you divide by 0. So in this case, we can plug in any number to this function except 0. So the domain is all numbers except for 0. And well, what about the range? Well, if we sketch a graph of this function over on the side, it looks something like this. And you'll see that if we get close to x equals 0, the function goes up towards infinity on the right side and down towards negative infinity on the left side. So it'll actually hit almost every number, except for it never quite touches the x-axis. So the range is also all numbers except 0. Okay. So that's a quick recap of how functions work. The next thing I'd like to look at is inverse functions. So we say that a function f of x is invertible if there exists an inverse function which usually is denoted by f to the -1 of x, and it has the property that if we take the inverse function and apply it to the original function, then we get back just x. Or another way of saying this is if y equals f of x, then f to the -1 of y should equal x. And so roughly speaking, what's going on is the inverse function undoes what the original function did. So if we plug a number into our function and then we apply the inverse function to that, we get back the original number that we started with. So what are some examples? If we take f of x to be the function x to the power 3, then the inverse function is going to be the cube root of x. And we can quickly check this, because if we check this property, then f of x will be x cubed, but then when we apply f inverse to that, we'll take the cube root, and we'll just be left over with x like we started with. Okay, another example. F of x equals 1 divided by x. So in this case, it turns out the inverse function is also 1 divided by x. How can we check this? Well, if we take a look at this property for inverse functions, we'll see that f inverse of f of x is 1 divided by 1 over x. And if you apply properties of fractions to this, you'll see that you flip the denominator and bring it to the numerator, and we're just left over with x. So these are two examples of functions that have inverses. So we say these functions are invertible. So one quick way you can check if a function is invertible is with the horizontal line test. And this says that a function is invertible if every horizontal line intersects it exactly, or at most one time. So it doesn't have to intersect the graph of the function, but if it does, it can only happen one time. So for example, if you look at the graph of f of x equals x cubed, then you'll see that it looks something like this. And if we draw horizontal lines, they never hit the function more than one time. So this function passes the horizontal line test, and it is invertible. On the other hand, if we take a look at the function f of x equals x squared, then we have a parabola. And if we draw some horizontal lines down here, they don't hit the graph at all. But if we draw one up here, then it hits the graph 2 times, and therefore this fails the horizontal line test, and the function is not invertible. And this again has to do with the fact that when we take the square root, we have a plus or minus sign, and that's what leads to this problem. Alright, so one more thing that's important to know about inverse functions is how we can obtain them given some formula or given a graph. So one thing you've probably seen in previous math classes is that if we are given a formula for some function, we can find the inverse function by switching the roles of x and y. So for example, suppose we want to find the inverse of the function f of x equals x minus 2 over x minus 1. Well, how would we do that? We would first write this as y equals x minus 2 over x minus 1. And then we would switch the x and y. And what this gives us is x equals y minus 2 over y minus 1. And if we rearrange this, you'll get yx minus x equals y minus 2. I multiplied both sides in this equation by y minus 1. And then if I move all the y's to the left-hand side and everything else to the right-hand side, this will give me y times x minus 1 is equal to, let's see, negative 2 plus x, it looks like. And then if I divide by x minus 1, I get that y equals x minus 2 over x minus 1. I feel like I've made a mistake somewhere. This isn't what I got in my notes. Let's see. So you move this to the other side. Yx minus x equals y minus. Factor out the x. Alright, bring y to the other side. So we get x minus 1 equals 2. Okay, so I don't see that I've made a mistake, so this seems to be all right. Yes, okay. So this would be our inverse function. So f to the negative 1 equals x minus 2 over x minus 1, and we get back the same function we started with again, which usually you will not, but it just happened to work out that way this time. Okay, so the general procedures, to recap, is you take your function, you switch the x and the y, and then you try to solve for y. Sometimes this can be difficult. For example, if we have a function which is slightly more complicated, so f of x equals x cubed plus x. So this function is invertible. We'll see roughly what the graph of it looks like in a minute. But if we try to use this trick, so we'd write y equals x cubed plus x, and we'd switch the roles of x and y to get x equals y cubed plus y, then trying to solve this equation for y is very difficult. So sometimes it's better to have a way to find the inverse function graphically. And so the usual trick that you use is to notice that when you switch the roles of x and y, really what you're doing to their graph is reflecting it across the line y equals x. So if I have a graph of my function, this thing here, roughly speaking, does something like this. I didn't actually check the graph, so it might not look exactly like that, but it's always going upwards, so it does pass the horizontal line test. So what you could do is sketch in the line y equals x. And then you would reflect across this line to get something like this. And so this would be f of x, and the reflection would be f to the negative 1 of x. So even though we don't necessarily have a formula for this inverse function, we can still get an idea of what it looks like by using this idea. Okay, so now that we've talked a bit about inverse functions, let's look at some different types of functions that we're going to encounter in this course. And I'm really only going to focus on 2 types of functions right now, but there are several that are going to be important. So there are linear functions. So you're probably familiar with these. They look like y equals mx plus b. So you should know how to, for example, find the slope, find the y-intercept, use point slope formula to find equations of lines. I'm going to assume you already know all of this. If you're not familiar with some of that, I recommend that you review. Another important type of function are polynomials. So for example, y equals x cubed plus x squared plus 2x minus 1, etc. Basically combinations of powers of x. Again, I'm not really going to talk about these. You should know how to factor some of the simpler polynomials like quadratics, how to find the roots of a polynomial equation if it's relatively simple or if it's factored, for example. But I'm not really going to talk much about these now either. Another important class are rational functions, which are fractions which have a polynomial in both the numerator and denominator. So for example, you might have x squared plus 1 over x minus 2. So there are plenty of functions of this class. And I'm not really going to talk about those either. but you should be familiar with how to find horizontal and vertical asymptotes and some things like this. And we will maybe touch on more of this later, but I'm going to assume you're relatively familiar with rational functions already. There's also trig functions, like sine of x, cosine of x, etc. We're going to talk about these later in the class. So for now, let's just not worry about trig functions. And so the two types of functions I do want to talk about, though, are exponential functions and logarithms. So let's start with the exponential functions. So these are things where we have some constant number raised to a variable power. So for example, 10 to the power x, 2 to the x, we could have 3 to the x, etc. So basically they all have the form a to the power x, where a is a positive number. And so let's take a look at an example of one of these functions, specifically 10 to the power x. So if we just take a look at what are the values for some different values of x, let's say -1, 10 to the -1 power is 1/10, 10 to the 0 power is 1, 10 to the first power is 10, second power is 100, third power is 1,000, and so on. So if we take a look at a graph, we can see the general shape of these functions. As they go towards the left, they get really close to 0, but as they go to the right, the function grows extremely fast. And this is known as exponential growth. So basically, exponential functions are some of the fastest growing functions that we'll see. So you probably saw in some previous math class that exponential functions have a lot of nice properties. And these are some things that you should be familiar with, so I'll just list a few of them for you. So the first one is that a to the power 0 is equal to 1. So anything we raise to the 0 power, we get 1. Also, we can have a to the x times a to the y is going to be equal to a to the x plus y. So if you multiply two exponentials with the same base, then you can add the exponents. And similarly, we have a to the x over a to the y equals a to the x minus y. And then the last property that we're going to use is that if we have some exponential function and we raise it to some power, then we get a to the b times c. Just a word of warning with this property, if we put the parentheses the other way, then this is no longer true in general. So be careful of that. Make sure that it really is this top one that you're using. All right, so then we might ask, okay, we now know about exponential functions, and we know how to find inverse functions, so can we find an inverse to the exponential function? And this leads to what are known as logarithms. So these are the inverses of exponential functions. So, Okay, so let's suppose we have some exponential function like y equals 10 to the power x. And we want to know what is the inverse. Well, we could try to use this trick that we saw before where we flip the x and the y, and we should have the x equals 10 to the y. But it would be pretty hard to solve this equation for y using standard techniques that like just algebraic manipulations. So we need to define a new quantity to handle this sort of equation. So we say that y is equal to log base 10 of x if it satisfies this equation. So if 10, what do I want to say? Yeah, so 10 to the log base 10 of x should give us x. So in other words, log base 10 is the inverse function of the exponential. That's probably hard to read. Let me write it bigger. And so, okay, if it's not an obvious number, like for example, if x is 100, then we know that y should be 2, because 10 squared is 100. But if x is like 20, then it will be hard to figure out y without a calculator. We can still get an idea of what these log functions look like by using the graphical approach. So we know that 10 to the x looks something like this. And so if we draw in our line y equals x, this is not the greatest drawn figure ever. It shouldn't actually hit this line. So it should be more like something like this. Then if we reflect this across that line, we'll get something which looks sort of like this. And this graph down here is y equals log base 10 of x. And similarly, we can find log base 2 of x is the inverse of 2 to the power x. Similarly for 3, 4, 5, and in general, we say log base b of x is the inverse function of b to the power x. So similarly to the exponential functions, there are a bunch of properties that are useful that go along with these. So first off, because we know that this is the inverse function of the exponential function, since a to the power 0 is equal to 1 for any value of a, we know that we're always going to have log base a of 1 is equal to 0 for any a that we pick. And similarly, all of these properties up here for exponentials will have a corresponding property for logs. So log of AB is equal to log of A plus log of B. Log of A divided by B is equal to log of A minus log of B. And maybe one of the most useful ones is that if we have log of a to some power, then we can bring the power outside of the logarithm, so we get x log of a. And this one is very useful for a lot of things. So let's do an example of how this might work. So suppose we have some equation like y equals 3 times 10 to the power x. I want to solve for x. Well, we have to get the x out of the exponent, so you would take the log of both sides. And with this property, I didn't write bases, but you can put any base you want on there. But I'm going to use log base 10 because that's what I have here, a 10 to the power x. So we'll see that the log base 10 and the 10 will cancel. So if I take log base 10 of both sides, then if I apply property 2 here, I can split this up into a sum of 2 logs. And then by applying property 4, I get the log base 10 of 3 plus x log base 10 of 10. But log base 10 of 10 is just asking what number do I have to raise 10 to get 10, and that number is 1. So really the equation that I get is just x plus log base 10 of 3 is equal to log base 10 of 4. And if I rearrange this, I get x is log base 10 of 4 minus log base 10 of 3. So that's how you can use these properties of exponents and logarithms to rearrange things. Okay, so probably that's everything that I'll be able to get to in the class. But I do want to talk about one more thing in case I have time to get to it, and it will come up later. If we don't get to it in lecture, then I'll probably talk about this when we need it later in the class. But that is even and odd functions. So just to give you some definitions, we say a function is even if f of negative x is equal to f of x for all x in the domain of the function. And a function is odd if f of negative x is equal to negative f of x for all x in the domain. So what are some examples? The function f of x equals x squared is even because if you plug in negative x, then when you square the negative, it goes away and you just get back x squared. And if you look at the graph of this, you'll see that it has symmetry if you reflect it across the y-axis, and that's a key property of even functions. On the other hand, if we look at the function f of x equals x cubed, this is an odd function. And the graph of this function looks something like this, and it's symmetric when rotated about the origin. Rotated 180 degrees. So if we take this thing and we just rotate it around like that, then we'll get back the same graph. So that's what this means. And that's a key property that you'll see with odd functions. So some functions are neither odd nor even, but if you do have an even or an odd function, it has these nice symmetry properties, and we'll see that that can be useful in some problems later in the class. Okay, so that was just a quick review of some things about functions. It was by no means comprehensive of everything you probably saw in earlier math classes, but I just wanted to refresh your memory about some things that are going to be useful.